Swayam Prabha. Digital India. Educated India.
We have discussed the first law and the second law in class. I am going to discuss some illustrative problems. The first problem I want to discuss is about historical measurements of the mechanical equivalent of heat. The experiments that were done by Rumford, Mayer and Joule. The numbers I am going to give you are equivalent numbers, and they are only illustrative and do not reflect the care with which original measurements were made. There is a book called The World of Physics by Weaver, Simon and Schuster 1987. I would recommend that you look at it for details. In each of the cases, what I wanted to do is to calculate the mechanical equivalent of heat. So, the first experiment was by Count Rumford in his cannon boring experiment, as it was called. He demonstrated that a horse working for 2.5 hours could generate enough heat by friction to bring 12 kilograms of water at 0 degrees to its boiling point. The horsepower is a vague unit. You can take 1 horsepower to be equal to 0.75 kilowatts, which is the current unit of measurement, current definition of horsepower. Second experiment was due to Mayer, who showed that the falling of a mass through 365 meters can raise the temperature of an equal mass of water through 1 degree C. Now, the third experiment consists of the famous paddle wheel experiments by Joule between 1840 and 1815, who demonstrated that on an average 2.32 watt hours of work produced a temperature rise of 0.56 degrees in 3.565 kgs of water. Joule also showed that using 12 volts across a coil fully immersed in water and passing 3 amps of current for 5 minutes raised the temperature of 180 grams of water through 14.3 degrees. So, in each of these cases we will calculate J, the mechanical equivalent. Take the experiment of Count Rumford. We are given that 1 horsepower is 0.75 kilowatts. Now, I am just calculating the work done by a horse in 2.5 hours. This is number of horses, 2.5 is hours, 0.75 is kilowatt by horsepower, then this is seconds per hour. So, if you multiply these out, you get kilowatt seconds or kilojoules, you get 6750 kilojoules. Now, the heat generated as a consequence was given by, in the experiment it is given to you, it is given as 12 kilograms times 1 kilocalorie per kilogram degree C, and this is degree C. So, you get simply 1200 kilocalories. J is simply W by Q. So, if you divide this 6750 kilojoules by 1200, you get 5.625. You can see this is a bit high, but Count Rumford himself used a little lower value than 0.75 as the conversion factor from what is now called the kilowatt unit to the horsepower. In any case, he got a number. Conceptually, this was one of the first demonstrations of the equivalence of heat and work. Now, Mayer did this experiment again. He reported that a given mass falling through 365 meters. So, you have mass, let us say in kilograms, this is meters per second squared. So, you get kilogram into meters per second squared newtons, and this is meters. So, Newton meter being a joule, he gets essentially 3580 m joules as the work done. The corresponding heat generated is given by, again the mass is in kilograms, this is kilocalories per kilogram degree C, this is degree C, this is 1000 is the conversion from kilocalories to calories. So, this gives you 1000 m, because he said an equivalent mass of water. So, J according to Mayer was simply W by Q, which was 3581 by 1000 came to 3.58. This is lower than the current value that is accepted, which is about 4.18. Then there were the experiments by Joule. So, Joule's paddle wheel experiments are the most famous. You may recall that he actually did this experiment repeatedly in the Royal Society, till the members of the Royal Society actually protested and said, we are convinced, do not do any more experiments, but Joule insisted that he do experiments in various ways. The paddle wheel experiments essentially consisted of having a paddle wheel, a container and a paddle wheel. This paddle wheel was rotated through a system, a complicated system of pulleys and ropes, etc., and a weight finally. This weight could move up and down, and you must remember that Joule did his experiments with great care. He accounted for convection loss, radiation loss to the environment, accounted for the elasticity of the rope, he accounted for the kinetic energy of the weights hitting the ground, and so on. And that world of physics reference that I told you about, these are given in detail, and this whole thing was an arrangement of pulleys and ropes. Okay, now let us get to his experiment. His experiment said that the total work done was 2.32 watt hours. This is watt hours, this is seconds per hour. So, if you convert it into watt seconds, which is joules, it will give you 8352 joules. Found that 3.565, which is kgs of water, this is kilocalories per kg per degree C, this is degree C, and I am multiplying by 1000 in order to get calories. So, you get 1996.4 calories is equivalent to 8352 joules, or the mechanical equivalent of heat is 4.184. This is as close to the currently accepted value as you can think of. Now, let us look at another experiment that Joule did, but I must emphasize here that you really have to read the original experiments and the care with which Joule did these experiments, because Joule was the first one to assert that while it was known that work and heat were the only two ways in which a closed system can exchange energy, while it was known that work and heat were two ways of exchanging energy with the surroundings for a closed system, Joule is the one who first asserted that there are only two ways. To make that assertion, he needed to show that work done in any form was equivalent to heat, and every form of exchange of energy was actually either heat or work. Now, let us look at another experiment that Joule did, and this was an experiment with an electric current. Joule had 12 volts, he had 3 amperes passing through the circuit, he had essentially a container with water, well stirred maybe. More importantly, he passed a current through it. So, he passes 3 amperes through a 12 volt circuit. So, you get this, and this is for 5 minutes. So, this is seconds. So, you get essentially watt seconds, which gives you joules. So, it is 10,800 joules was the work done by the current passing through the circuit for 5 minutes. Now, the corresponding increase in water temperature is given, and the weight of the water is given. It is 180 kilograms. This is kilocalories per degree C per kilogram, and this is degree C. So, what you get by way of Q is simply a total of, I am sorry, the experiment was simply grams, not kilograms. So, here you are talking about calories per gram, and the total amount here you get is 2574 calories, and J is therefore 10,800 divided by 2.574, you get 4.19. Again, you have to read the original description of the original experiments to appreciate the accuracy, the methodical way in which Joule did these experiments. And when you are a pioneer, it becomes that much more difficult, because you have to be extra careful. It shows a certain perseverance and faith in the scientific process. Then let me now get to a second problem. We can discuss both closed and open systems in class, and you can calculate the work done in different situations. And here we are going to look at a pump that works adiabatically. This is a pump. Okay, at the inlet, this is 1 kg per centimeter squared, and the outlet is given as 10 kg per centimeter squared, and the flow rate is given as 10 liters per second. Okay, you should realize that the pump itself, if you look at it in cross section, is driven by a motor . So, this is the input to the pump, this is the outlet, and this is the motor working on the pump. So, the question is, how much horsepower should the motor have in order to do this job? Horsepower or kilowatts? What should be the power of the motor? So, it says the pump works adiabatically. It is required to pump water at 25 degrees and 1 kilogram per centimeter squared to 10 kilogram per centimeter squared at the rate of 10 liters per second. At constant entropy, the specific volume varies with pressure. This comes from painstaking measurements of the equation of state. You get an expression V is equal to 1025 minus 0.5076 P, where V is in centimeters per kilogram, centimeter cube per kilogram, and P is in kg per centimeter squared. So, you are asked to calculate the rating of the motor pump, motor driving the pump in kilowatts. So, we have to define a system. We define the system as simply the contents of the pump. Here we are saying the contents of the pump, you essentially analyze the system for a time long enough, so that this is less than total water flowing through. It says 10 liters per second. So, you are talking of even if you are talking of 10 seconds, you are talking of 100 liters going through, and the size of the pump is much smaller. So, what the pump contains is small mass, whose small mass of water, and the mass can be neglected in comparison to the mass of water flowing through during the period for which the analysis is done. Or you can discuss the operation of the pump at steady state. So, it is either steady state or negligible hold up. Hold up is what is contained inside the pump. Now, you can write the two laws. We have written this in class for an open system. it says adiabatic. So, this has to be 0. You are interested in calculating this because of the negligible hold up or the steady state assumption, this is 0. So, you simply have at steady state 3 terms, of which dm in is equal to dm out. So, if you take Ws dot by m dot, the rate at which work is done divided by the rate at which mass is flowing through the system, you simply get minus of delta H. You take these two to the other side, is H out minus H in. So, Ws is equal to plus, sorry, this is defined as H out minus H in. You can calculate H out minus H in from again the equations of thermodynamics. You have dH is equal to delta Q plus V dP, you are looking at PVT systems, and here delta Q is given as 0. So, dH delta H is simply the integral over V dP from P in to P out, which is from 1 to 10. Some conversion involved, because this expression that is given to you in the problem statement gives you the volume in centimeter cube per kilogram. The pressure itself is given in kilograms per centimeter squared. So, you get this is kilogram into centimeter, these kilogram and kilogram cancel, and when you do the VdP calculation, this is kilogram per centimeter squared pressure, this is the pressure should be multiplied by 9.81, which gives you meters per second squared. So, this is the actual pressure, kilogram meter per second squared will give you newtons, it will give you in newtons per centimeter squared. So, essentially this centimeter is converted to meter here, this is meters per centimeter, and finally you are dividing by 1000 in order to get kilojoules. Out of this you get joules, and this is the conversion from joules to kilojoules. So, the result you get is simply 0.97 kilojoules per kilogram. Now, this is liters per second, this is the density, which is kg per liter of water, into the work done per unit mass, which is simply 0.97. So, you get 9.7 kilowatt. So, this is the rating of the pump that you need for adiabatic operation to pump 10 liters per second of water from 1 kg to 10 kg per centimeter square. I would recommend that you get an idea of the order of magnitude of this by looking at the rating of the pump, maybe in your house, where the water is pumped from the tank underground to the overhead tank. So, this is a second example where we calculate the work done by the pump, and we have assumed adiabatic. Effectively during the process of pumping, the time is rather short for much heat to be exchanged in the surroundings. Besides, the temperature difference is also small between the pump or its contents and the surroundings. It is a very reasonable assumption. So, you get the rating of the pump directly. This is Ws dot, if you like, you get Ws dot here, which is the power. Let me take a third example. All of our big cities are short of power, and one suggestion is that you could set up a power plant on the banks of a river. In this case, we are talking of Chennai. I am looking at the river Kuam. In order to set up a power plant, because Carnot has told you that if you start with energy at temperature T1, you need a temperature T2 to which you have to reject heat you draw heat at T1, reject heat at T2, and you can get work at most equal to T1 minus T2 by T1 into the amount of heat drawn. Now, the amount of heat drawn is one constraint. Another constraint could be the amount of heat rejected. So, if you have, for example, let us say you have a river flowing, you have a nuclear reactor, so you are drawing heat from it, you are rejecting heat here and you are doing work here, right. This W is related to this amount of heat rejected here, or W dot is related to Q2 dot. Now, what you are asked is, because of pollution considerations, you are told that there is this river here, the Coombe river in this case, in which the flow varies seasonally, and in all seasons you are allowed to pollute the river thermally to the extent of 1 degree centigrade. For example, in the dry season it runs at 30 degrees C at 2 meter cube per second. So, you can go from 30 to 31 degrees. Beyond that you will affect the life in the river. Similarly, in the wet season, for example, the water is at 25 degrees and the flow is at 8 meter cube per second. Again, you are allowed to pollute it to the extent of 1 degree. You are asked to calculate what is the maximum power. Now, you go back to Carnot. Carnot tells you that this reactor here, in this case, is at 400 degrees C, and this temperature varies with the season here. This is T2. So, if the reactor temperature is T1, it is equal to 673 degrees Kelvin. Now, W dot by Q2 dot is, if you like, Q1 dot minus Q2 dot by Q1 dot, but this is equal to T1 minus T2 by T2. That is what Carnot has told. Now, T2 can vary with season. So, you are asked to calculate in 2 seasons what is the amount of work that power that you can produce. The dry season flow rate is given as 2 meter cube per second, and the temperature you have already been told 30 degrees, which is 303.2 degrees K. So, you can use this formula. You know, W dot by Q dot is simply Q1 minus Q2 is W dot divided by Q2, which is T1 minus T2 by T2. So, if Q2 dot permitted is now given to you, it is given as 2 into 1000 into 1, this is simply meter cube per second, this is kilograms per meter cube for water, this is the specific heat, which is kilocalories per kilogram degree C, and the thermal pollution allowed is 1 degree C. So, if you multiply these out, you get 2000 kilocalories per second. This is the permitted thermal pollution. If this is all the heat you can reject to the river, then the work produced is automatically constrained by the formula that we already showed. You have, this is T1, this is T2, and this is T2. T2 actually increases by a degree, but does not make a difference here. So, you put this in and ask what is the work you can get. This is joules, conversion joules per calorie or kilojoules per kilocalorie. So, you get out of this, you get power, and you have to divide by 1000 to get megawatts. This is joules per second, because this is calories per kilocalories per second. So, if you like, this is kilojoules per kilocalorie. So, if you convert this, this is megawatts, conversion to megawatts, or if you like, it is megawatt per kilowatt. which is 1 by 1000. So, you get 10.2 megawatts. In the monsoon season the flow rate is 8 and your temperature T2 changes to 298.2. So, you get the same figures, it is slightly different, 8000 instead of 2000, same formula. The temperature T1 is the same, T2 is now replaced, 303.2 is replaced by 298.2, and then you have 4.18, the same conversion factors, you get 41.2 megawatts. So, it is a fairly straightforward calculation. We have seen 3 illustrative problems. One is to follow the measurements of the masters to see what conclusions they came to. The second we looked at a problem of pumping water, which is a normal day to day problem under, in this case under adiabatic conditions. And the third problem that we looked at was simply the problem of power generation using both the laws. What is the maximum power you can generate if you are constrained by the thermal pollution of the sink. So, I hope these problems have illustrated for you the power of the thermodynamic theory that we did in class. I will stop there. In the next class we will discuss, next session on tutorials, we will discuss some or more of the theory that we discuss in class. Thank you very much.